I'm Eyal Amir. And is this on?
Yeah.
Okay, good. I'm right now a professor at the University of Illinois at Urbana-Champaign, and I'm going to give you a talk about some of my work and, of course, some of my students' work. And Megan here has done some of the stuff that you will see as well. So I'm going to talk about how to learn. So I assume that I'm given a sequence of actions and observations. I see somebody, say, behind somebody's back. I'm looking at what the user types, and I see what action the user makes on, say, a web page. I click a button, and I see what happens. So I see the user took an action, and then I see that some effect happened. And what I want is to estimate how the actions that the user is doing, how they affect the world. So for example, I want something like A is executable if the state satisfies some property. And I want to find out if, under some condition, this action A causes some effect. So I'll give you an example. This is a small demo. And I'll explain here a little bit what I mean by this learning problem. So what you see here, there's an adventure game here that is kind of in the background. It's a simulation, really. Here there is a sequence of actions taken from kind of the higher the action, the more recent it is. So for example, here's an action number 11, get mouse in room 3. And then action 31, which is the current one, go south from room 1. Okay? These are actions that our agent is performing. And what you see on the right, you see a table. Unfortunately, it's cut a little bit here by the architecture of the room. But let me show you a little bit here. I think you can now see the fraction of the table. So on this column, you see a set of actions, so such as go north from room 2. And on the columns, you see the features that the agent sees in the world. So for example, the agent is in room 0. We have a kind of, just an adventure game where an agent performs different actions, like picking up keys, flipping light switches, and so forth. And the agent sees all kinds of things in this world and decides how its actions affect the world. So what you see in this table, an empty, kind of a black rubric is a place where we don't know, the agent doesn't know anything about the world. A block where it says causes not, say, go east from room 0 causes the agent not to be in room 0. So the agent knows for sure that this is the effect of this action on this feature. For example, another thing that, say, go north from room 2, the agent knows something, but it doesn't know for sure what the action is doing. It knows that the action either causes the agent to be in room 0 or it keeps the value of being in room 0. Okay? So, by the way, you can stop me at any point. I can kind of make the presentation shorter or longer as you wish. So if at any point you kind of lose what I'm saying, just interrupt. Okay?
So do you have partial observability of the current state or only of the action results?
The current state. The entire, I see, I don't even have a real expectation on what I will see. The observation model is whatever you see is correct, but you can't predict what you will see as a result.
So it seems odd that you have action names like go east from room 0 rather than go east.
That's right.
If you don't know what room you're currently in.
That's right. Oh, okay. So if the, sorry, so the question was that it's odd that I have all of the parameters here specified in the action as I'm doing the action. And it is correct. We have, this is kind of, we're in progress of research, and what we're doing, there are some, I can talk a little bit more about how to enlarge this or kind of expand this to cases where you don't know those parameters. What we currently do, and this is actually something that Megan is also working on, is introducing new variables as if about what we don't know. Okay, so so you can make this a little more general. Okay, in the most general in some senses, we would like to know something about what going east from room X causes us, and maybe we'll generalize that. And I will show also some experiments on that at the end. Okay, so this is the kind of stuff that I would like to handle, and really, so what you've seen is really an instance of this kind of sequence of events. So we see some the agent entering a certain room. The agent is performing some actions like flipping a switch, going west. We get some text back, and going east is the next action that the agent is performing, and we see some text in return as well. Okay, so those are the kinds of things that I will receive. In the simulation that you've seen, I didn't have any natural language text, and I'm not going to talk about text in the rest of this talk. Okay, why is this important? There are many applications for solving this kind of problem. We have an agent acting in the world. Say it could be the World Wide Web, it could be a mobile robot, it could be some game-playing agent, it could be that we had software that wants to interface to a new version of an old software. So we want this software to adapt by experimenting. So it can perform an action. It doesn't see really how its actions affect the world, but it sees some observations. And we want the agent to try to figure out from those observations what the actions are doing. And the difficulties are really that we don't have a knowledge of how the actions affect the world a priori. There are many features in the world, and the domain is partially observable. So in the rest of the talk, I'm going to tell you more formally what it means for actions to change the world in a partially observable domain, how we represent this change and update the representation that we have in an efficient way, and then I'm going to talk about some related work and conclude. So here's a picture of how the problem can be seen. What you see here is the state of the world, although this is the same globe. It actually means a different world state. So the world progresses in response to our actions, and we make some observations. Those are those arrows that go up. What you see here, noted as K1, K2, K3, and so forth, this is some sort of a knowledge that the agent has at that particular time. So after the agent performs an action, it knows that it performed that action, and it makes some observations, and we now have to update its knowledge state. Now, what complicates this matter is that this transition relation at the top, that is also not known, and the agent needs to kind of have a state estimator that combines both the transition relation, the lack of knowledge of the transition relation, and the state of the world. Okay, so what our task is here is to be able to update our knowledge about the transition relation and the state of the world at the same time, and this is what we're going to do. So we're going to try to do this update in an efficient way so that at the end we have the most correct picture that we can have. Okay, so here is a very, very, very simple example that I will use in the rest of the talk. It's from this adventure game world. What we have are two rooms here, and really three features in this world. Whether the agent is in room east or room west, whether the switch is up or not up. Here, this tilde here means not. Okay, so the switch is not up. And here the light is not on. Okay, so the switch is in the east room, the light is in the west room, and our agent is in the east room, so it doesn't really see the state of the light. It can see the switch. It knows that it's in the east room, but it doesn't see the state of the light. Let's say that now the agent is performing a very simple action of flipping the switch. So now it sees that the light that he's still in the east room, and the switches up, but it can't see what the state of the light. This is what happens in the real world, but the agent doesn't know that this is the real world. So what should the agent do? The agent really could represent its state of knowledge with this set of pairs. Each pair has a transition relation and a possible state. Okay, and we have a set of those. When the agent performs an action, it knows that as a result of the action, if this transition 3, this is the model of the change in the world, if that was indeed the transition model that governs the world, then in the result of the action, the agent will be here. Okay, the agent will be in this particular state and still will have the same transition relation. Okay, and the same goes with the other transitions. If this is a non-deterministic transition, say T3, then world 2 will split into, there are many possible outcomes for this action that the agent is doing. When the agent makes an observation, it can cross off a few of those pairs, and this is really the process by which the agent decides what are the possible transitions in the world. Okay, only T2 and T3 are those that are possible right now. The problem with this kind of representation is that if we are talking about n-world features, then the size of those sets could be very, very large. And especially if we want to scale this to n's that are in the thousands or millions, this is completely useless. So, for example, even in our simple example here, when we had the light switch and being in the east, west, and so forth, we start with a very large belief state. Okay, these are the two possible states on the left here, and on the right we have all the possible transition relations. After we apply this action of, say, going west, we will have this kind of very long list of possible combinations of world state and, say, transitions that map the state to the same state, transitions that change the state in a particular form, and so forth. After we make an observation, say we observe that the agent is no longer in the eastern room and the light is not on, we will cross out a few of those, but we will still have this very large set that we need to represent. Okay, so that was the problem, really, being able to do this update, but without representing those states explicitly. And what I'm going to do now is I'm going to use formal language to represent the possible states, the possible transition relations, and I will show you how to update in that formal language. Yes?
So I'm trying to understand where the uncertainty is in this model. So, for example, when I take an action, if I had perfect knowledge, would I know the state of the world, or is it some non-determinism in the underlying results of the action?
Sorry, the question was whether the lack of knowledge here is in the state of the world or the possible effects of actions.
Is it fundamental non-determinism, or if I had perfect knowledge, would everything become deterministic now?
Okay, so the question again, just I repeat it for the viewers. So the question is it that is there a fundamental non-determinism here, or if I knew the transition relation, would all of those transitions be deterministic? Yes. So for the rest of the talk, I do assume that all of the transitions are deterministic. So if you knew how the actions affect the world, then everything would be deterministic. That's right. Yeah. Okay. So the way that I'm going to represent those sets, I'm going to devote for this like a few minutes. The way I'm going to represent the sets is just by a logical formula. In this very simple case, I'm going to use a simple propositional language where I have propositions that talk about world features and propositions that talk about how actions affect the world. So for example, I will have a proposition that says that switching flipping a switch up causes the light to go on, the switch to be up, and the state of if the agent is in the east room. Okay, so I will have a proposition that says that. I will also have a proposition that says that going west keeps the value of the switch, the position of the switch. Okay, and I will have some propositional symbols that I denote like this. So switching up causes the light switch to be up if we are in the east room. That could be a proposition in my language. Okay? So for example, if I had this light switch example from before where I had this set of possible pairs, okay, all the states and all possible transitions, then right now I can just write it with this very simple logical formula that says I'm in the east room and the light switch is not up. And this is all I know about the world, and this will represent for me the state of my knowledge. Okay, so now the question is really, how do we update this new representation? And who tells us that this new representation will not explode into the large size that we had before? So let me first tell you how I'm going to update this representation. And I'm going to give you 2 slides of theory, and then I'm going to go into algorithms that are more efficient. The theory is this. We have a logical representation that tells us what we know. We also have a piece of knowledge that tells us how the world is updated if some conditions are met by our transition relation. So for example, I can say, I have a logical formula that tells me this kind of how the actions will react if they have certain properties. And from that, I want to conclude things like, if after the action I'm in the east room, then it must be that flipping the switch up either caused me to be in the east room, either it keeps the value of being in the east room, or it causes me to be in the east room. If I will now observe that really I'm in the east room after doing this action, then either it was true before that I was in the east room and the action just didn't change it, or the action actually changes it in a certain way, and that is the way. So I'm going to make the agent be in the east room. Okay, so these are the kinds of things that I would like to conclude from my logical formula here. And I'm not going deep into what that logical formula is, but if you're interested, I can. Yes?
Are you able to represent things like, if the switch is on and I go east, then I end up in this room, but if it's off, then I end up somewhere else?
Yes.
So
Yeah. So the question, I'm sorry, the question is, can I represent conditional effects? Or effects like, if this is the state of the world, if the main switch is on, then the light will go on. But if the power company does not supply any power, then I will not have the light go on. Yeah. I'm not showing this here in this talk, but not in the examples that I have, but the implementations that we have right now. And maybe I will show it a little bit in a few minutes. It will be something closer to what you're thinking about. But yeah, what you need to do that is just to have more propositions. Really, that's really the effect that you have. The more conditional effects that you allow, the larger, the more complex the conditions are, the more complex your algorithm will be in terms of time.
And you expect that essentially to be an input into your algorithm, sort of how complex the conditional effects can be?
So the question is, do I expect an input to my program that says how complex the conditions are? And the answer is, right now we do. It is relatively easy to change it to something that adjusts automatically. You can kind of say, well, if I don't have any models that say that this is with this k preconditions, I don't have a solution, then I can just expand it to k plus 1 automatically. Okay, so let me come back to just the kind of the main theoretical story. The main theoretical story is we have a representation in some logical formula, propositional logical formula in this case, that represents what I know about the state of the world and the what I know about the effects of actions. And I am doing some sort of update of that formula by knowing that the action has occurred, and then by knowing that the observation is seen. Okay, so before I move forward, just so that you know, it's very easy to show that this is really equivalent to representing the exact set of pairs. That's the important thing that we have to keep in mind. We're not losing any information here by moving into this new representation. Okay, so now I'm going to give you two algorithms. I'm going to focus on the first one, where we represent the knowledge as a directed acyclic graph, and if according to time, I will also tell you about a second one. By the way, how much time should I, when should I conclude?
12.
At 12?
11:50.
Okay, so with questions it'll be, so okay, so with questions we will be at 12. Okay, so I have about 20 minutes. Okay, so let me tell you how I'm going to do this update of the formula efficiently. And the way that I'm going to do that is I'm going to represent what I know as a DAG, directed acyclic graph, and this is how it's going to evolve. Let me just show you kind of the animation a little bit. But what happens is this. Assume that at time 0, I have some these transition rules here. So nodes that tell me that pressing a button causes, say, a door to be locked if it was not locked before. And another possible transition rule is pressing a button causes the door not to be locked if it was locked before. I don't know which of those is true. These are just propositions, and I actually have many of them in my representation here. This node here in the middle will be an explanation, if I have any, for having the door, for observing the door locked. So if I now knew, if I somehow observed that the door is locked, then this would be the explanation for me. It's just a node here. And after a few, believe me that after a few steps, say after t time steps, we have this DAG here that represents what I know about the state of the world and the transition rules. I know which one of them is true. This is, you can think about it as an NNF or a BDD, if you're familiar with those. It's just a graph representation that says this feature is true if, when I go down, when I evaluate this logical formula, I will actually get true. Or in some sense, it is possible, if there is a satisfying assignment for those features here, that ends up with the top node being true. Now, what happens when I do the one step? This is the algorithm. Really, we transition from time step t to time step t plus 1. This is an explanation for whether the door is locked, for the door being locked. Okay, now, the explanation at time t plus 1 would be either one of the two. The door could be locked if either lock was caused by my action. Okay, so this is this branch. There are many possible causes, and here is one of them. This transition rule is true, and it is not true that this feature held at time t. Now, on the other branch, this is the other possibility for the explanation. The door could be locked now because it was locked before and I didn't change the value of this locked. So what happens here is that this is AND of this node, the explanation that I had before, together with, it's not true that both this explanation holds and this feature is true. Now, of course, if you look at this a little carefully, I can do some simplifications. But my step here, the update step, is just adding those connective nodes. So this is an AND, this is a NOT, an AND. I added about 7 nodes here. Now notice that I didn't really add any new variables. I didn't really change any variables, and I didn't touch anything inside here, inside this cloud here that represented the DAG from previous states. Okay, this is really the main thing, the main technical thing of this algorithm. So if you have any questions, now's the time. It's a very simple step. What's interesting about this step? Well, why is this? Well, actually, let me first kind of go over the entire algorithm. What you do is you do this step iteratively. You take the knowledge that you have, you're given an action and observation, and you conjoin your knowledge base with the knowledge that this action is executable. There is a formula that will say that this action is executable, and then I will update the explanation of every feature. So I'm given the previous explanation and maybe explanations for other features, and I will update the new explanation, maybe with some connections to other features, and I'm going to replace the previous features with links to their explanations. So if I had the precondition of locking the door or pressing a button was that I will also be in the room, then I will have a condition that I'm in that room. But I'm not going to keep track of what was true in the previous time step, so I need to update that, and I'm just replacing it with this new explanation. I'm telling, OK, this precondition, if it was true, then it had an explanation, and I will link to that explanation. OK, so this is my one-step update, and I will also then conjoin my formula with observations. So this is the algorithm. And the interesting features of it are that it takes constant time to do the update, assuming that I use a hash table and assuming that really the constant time really is I should say really the constant time is constant times the number of features that you need to update with your action. The algorithm is exact. That is, we are not losing any models in this representation. And the DAG size is, at the end of t steps, is just t times some n to the k plus phi 0, where this k is the number of features in my action precondition. So that comes back to your question from before. If I have more features in my preconditions, really this representation will be larger. Okay? Where do we win? Why did we do all this complex, or kind of, why did we go through all this analysis? The algorithm is actually very simple, but why should we use it? The reason is that we really still have only n world features. And those are the features at time t, or time t plus 1, or after we did all of these, the sequence of steps. So we went through some combinatorial, kind of a combinatorial process that at the end, really, we have a representation of what is true at time t together with what we know about the transition relations. What do we do with that representation? We can use some stat solver to tell us, to give us a model, or to verify a query for us. And that's what we did in that demo that I showed at the beginning. So I can use a stat solver to just tell me, OK, what can I know now about the world? why is it better than to just use SAT solver on the entire representation? Just because that would be, it would take you time that is exponential in the number of steps that you performed in the world. You will have t times n variables that you will have to look at. Okay, here are some example experiments that we did. What you see is here, this is a graph that shows you how the algorithm updates the representation. There are 3 different lines for 3 different domain sizes. The green is with 19 features, 55 features, and 109 features. What you see here at every time point is the time that it takes to do an update of the formula for one step. Okay, so we see that this is over about 5,000 steps, where each step is another piece of data, another action got executed, another observation was seen. And what I want you to get from this slide is that really the time to do the update doesn't grow. So we maintain the same time to do the update. If we are going to go for 1,000,000 steps or for 1,000,000,000 steps, it will always be the same time. Now, the formula size does increase, but it increases linearly, because at every point in time, we add this fixed number of new connectives. Okay, we still have the same number of variables. The formula size increases with the number of connectives that we add. And again, what I want you to get from this is that this is linear. So if we go for 1,000,000,000 steps, then the size of the formula will be 1,000,000,000, or 1,000,000,000 times 3, maybe. And now we can ask, okay, well, we did all this update. Now, maybe in the process, you really made this formula useless. But what we did is we created a SAT solver. We meaning one of my students, Daphna Shachaf. She has created a SAT solver that runs on these kinds of DAGs. And what you can see from this is the time that it takes to do different inferences. So we ask different queries from that DAG after many steps. So this is up to 4,000 steps. So 4,000 steps into the future, we ask a question. And if we want to find a model, kind of in general, you will see the kind of the black circles here are the times in milliseconds that it takes us to answer a query. And what you see in kind of the triangles is what happens when we're asking a query about a rule, and that an action rule, and that turns out to be true. What happens, this is when we ask a question about rules and it turns out that the query is false. And what you see here in the yellow circles and here the diamonds, the green diamonds, those are the questions that we ask about the state of the world. So why is this important and interesting? The important thing about this is that while this, it does grow, it grows linearly. What that tells us is that the formula is not becoming more complex. Whatever our presentation is of the possible transition models, this is not a complex formula, and we can do, so perhaps it takes us more time to do the checking, but it's really time that is linear. The growth is really linear with the number of steps that I need to process. So that makes it feasible for us to run 10,000 steps because, well, in 10,000 steps, it'll maybe take me 10 seconds to run a query on the result. Okay. I have a quick, so I want to conclude with the first algorithm. So what I showed you is just one algorithm to update a logical formula that represents possible transition models and states of the world, I'm going to briefly show you how we can update a flat representation in some cases. I want to emphasize, though, that this DAG representation that I showed, assuming that your actions are deterministic, you can solve the problem with this DAG algorithm completely. I didn't make any other assumptions besides the assumption of determinism of the actions. Here, the second algorithm, I will make some new assumptions. And under those assumptions, I will also be able to show that the update is correct and the representation is compact. So here is the algorithm. It's a very simple algorithm. You take a logical formula that represents the possible states of the world and the transition models, and you break it into its literals, its different propositional symbols. Each one of the propositional symbols we're going to update separately by some table that we're going to generate beforehand, and the result representation is just the combination of those updates for, again, an update for each one of the pieces separately. Okay? This new formula is our new belief state. Okay, so here's a couple of interesting things about this algorithm. This algorithm takes time that is linear in the representation size that we have. It is exact when the actions map states one-to-one. So for example, if I press a button that transfers money from my bank account into my PayPal account, then if I transfer $50, then $50, whatever my account was before the action, it will now be $50 less. And whatever my PayPal account was before the action, it will now be $50 more. Okay, so that's a one-to-one action on the world. And so if this holds, then this algorithm is correct, and I will explain in a second why. And also, if I had actions that are not one-to-one, but if they had no conditional effects, then I could also do a similar update. Otherwise, I will get just an approximate result. So here is an explanation. Let me explain to you why mapping states is one-to-one. This is the last technical part of the talk. So what you're going to see if this process of breaking the formula into its pieces really is what we do is we take a formula, we say, okay, if this formula is built of a conjunction of, say, two formulas, and we update each one of them separately. What happens when we have a non-one-to-one action? So look at the example here at the bottom. We have two formulas, phi and psi. They correspond to two sets. Okay, so let's say that these two sets don't have any intersection. The intersection is empty, and so the update should, if I had no models before, I shouldn't have any models after the action. And that didn't change what I know. But if we update each one of them separately and then conjoin the result, what we have is maybe we will have a model that is now in the conjunction because the actions didn't map states one-to-one. When we have an action that maps states one-to-one, then it cannot be that the two sets will intersect after the action if they didn't intersect before the action. Okay, so this kind of insight allows us to say, well, if the actions are map states one-to-one, then I can break this update of a formula into an update of its smallest pieces. And since I have only n features in the world, and say I have m possible action rules, then this set of I can create a table of a relatively small size that will just tell me how to update each one of them separately, and that's what we do. Sorry about that. Okay, so this is it. So we have an algorithm that is exact and has some guarantees on the compactness of a representation after the action. I don't want to tell you too many things, too many details here, but just assume that I want to turn your attention to two things. First is, we know that if we can observe every feature every, say, k times, then the representation, we can keep the representation compact. So compact in the sense that the representation will be order of n to the power of k plus 1. So say if I want to check how my web page, what is the effect of transferring money by pressing a certain button, then I can go into some web pages and check that every, say, k steps. And I am sure that the representation of what I know is compact. That guarantees that the overall algorithm is tractable. OK. So here's a bigger picture of what I showed you. The bigger picture is this. We have an agent that really explores the world. What I talked about today is this learning module here that is joined with kind of filtering the state of the world. We interact with a knowledge base, and sometimes we will also include some common sense information together with the knowledge that we now acquired in the world. We use that to make decisions about what actions to take in the world. I didn't talk about how we decide what actions to take. It's a completely different talk. But we are going to make those decisions, and we're going to interface with the world model that'll give us the information that we need for the algorithm. OK, so let me summarize. What I showed is how to learn the effects and preconditions of actions in partially observable domains. I showed that we have an exact update algorithm for directed acyclic graphs. We also have a CNF update algorithm, kind of a flat representation of logical formulas that works if some conditions about the domain hold. And the important things about these algorithms is that the first one is exact for every action. We can update them efficiently, the models of those transitions, the set of transition models and world states. And the result representation is compact. And that's most important because we want to actually be able to continue this into the future and also to use the model. You may ask, what of this here is the work that my group has done? And the main contribution that we have done is to present the first tractable learning algorithm for partially observable dynamic domains. Now, we assume determinism here, which is a very strong assumption. This determinism assumption does hold in some domains, in particular the World Wide Web, at least in most cases that we were interested in looking at. We haven't really experimented with an agent that works on the World Wide Web. What we did was just in this simulated environment that I showed you at the beginning. But this is kind of the direction that we're going. What I want you to remember from this is really that the algorithm is always exact and optimal, and that it takes a constant update time. These are things that allow us to solve problems that have very large number of features, and we have generalized this to relational representation and a few other generalizations, like Peter mentioned at the beginning, what happens when you don't know what were the parameters for your actions. We have done something along those lines. We didn't finish this yet. This relates to many things that you probably are familiar with, reinforcement learning and hidden Markov models, and also learning AI planning operators. Just to give you an idea what would happen if I use a hidden Markov model to represent this, or a DBN to represent this. What would happen is that I will need to update the structure of the DBN, or I will have in this kind of using an EM-like hill climbing approach. And the size of the domains that I will be able to deal with, and at least this is, we didn't try it, all of the most kind of up-to-date things. We just looked at the papers. The number of features that people were able to deal with were usually at the order of tens. So say 10, 15, 20 features that govern your domain. And these were kind of the state-of-the-art approaches for learning the structure of DBNs. So it's true that their problem is much more difficult. They're looking at general stochastic processes. But if we want to solve problems that are large enough, then we have to make some assumptions and examine them. And perhaps from this, we can build and extend this to stochastic processes. And this is one of the things that we're looking at. So there are many interesting open problems, particularly the how do we do efficient inference with the learned formula, what to do, how to do the same thing for stochastic domains, and also how to use dynamic observation models. So if I had an observation model that would tell me what I should expect after I do a certain action, that should be included in this process. So I'm done. You can find some of the software on my website. And you can also ask me, of course, for the software, and I will be happy to send it. So I'll be taking questions now. Thanks. If you have any more questions.
What is the software that you have then?
So we have, the question was, what is the software that I have in the, on the website? We have a software for updating the, currently what we have is just a software for updating the representation of the possible transition models and the world state. So we have the second algorithm that I showed that's available on the web page. It's just implemented by, you give it some input that could be whatever you know about the state of the world as a logical formula. It could be an empty input. So I don't know anything about the current state. And you can just run it on, it's in a batch mode. So you give it a sequence of actions and a sequence of observations, and it will output the formula that represents how your states affect, how your actions affect the world. The other, the DAG algorithm that I presented, we should put it on the web very soon, like in a week or two. And I can also, if you're interested, I can send you the decision-making software too. We have a paper in ICAPS this year, Alan Chang and myself. He's a student of mine. Yeah. No? Thanks.